All right, guys, so we're ready for our next topic. I think we got electronic configurations down pretty well, so now we're going to do quantum numbers. The idea of quantum numbers is, when we talk about the different types of orbitals, the s orbital, the p orbitals, the d orbitals, and all that kind of stuff, we have to remember that while we can look at a picture of what the orbital looks like, we have to remember that it's a representation of a mathematical probability function where physicists are calculating the most likely regions of space where you would find an electron. So there's a lot of math behind all this stuff. And when we derive the equations, the math relates to there are four values or variables that the scientists will solve for. So we're going to talk about what they are and kind of what their values represent. So these are our quantum numbers. The four quantum numbers. The first one is n, is the principal quantum number. It basically represents the energy level. So whether I'm in the first shell or second shell or third shell, that's n equals 1, n equals 2, n equals 3. Okay? So n is the energy level. It's always going to be a positive whole number. N equals 1, n equals 2, n equals 3. It's always a positive whole number. Okay? So that's the principal quantum number. The next one is L. That's called the angular momentum quantum number. Now, again, the names of these, I don't worry about the names too much, but I'll be honest, when you take the national ACS exam at the end of the semester, whether they use the letters or the names, you have to kind of know what they're talking about. So make sure you're familiar with the names of each quantum number. But so the angular momentum quantum number is the one that defines the shape of the orbital. So this is the one that's going to determine whether you have an s orbital or a p orbital or a d orbital. Okay? So n is the shell or energy level. L tells you the type of orbital, s, p, d, or f. And remember that L can go past f. Theoretically, there could be a g orbital or an h orbital, or you could even keep going. Okay? Now, L's values, again, it's going to be a whole number, but L can be 0, and L can go from 0 all the way up, but it can never be as big as N. So like if N is 4, then L can be anything up to 3. So L can never be more than N minus 1. Okay? Then M sub L. M sub L is going to define, it's called the magnetic quantum number. It's going to define when I have a set of orbitals. So like let's just say if L equals 1, that's going to mean we're in a set of p orbitals. M sub L is going to distinguish the p orbitals from each other. Okay, so the p orbitals, there's always 3 of them. If there are 3 of them, that means I need 3 separate values for M sub L to distinguish those orbitals from each other. So M sub L, the range of values, M sub L can go from whatever, if L equals 1, M sub L is going to be any whole number between -1 and +1. If L equals 2, then that means M sub L can go from -2 to +2. If L equals 3, then M sub L can go from -3 to +3. Okay? So M sub L's values are going to be based upon L's values. Okay? And then finally, M sub S is called the magnetic spin quantum number, and that's just going to represent when we do our orbital diagram. And if you remember, we put the arrows, we pointed one electron up and one down in each orbital. So when we did that, we said they have opposite spin. Well, the values we're going to use for M sub S is going to be either positive 1/2 or negative 1/2. That represents the opposite spins that can occur. Okay. Now the values, like, why is it a half? That's just related to all the math that they do. Don't worry about that too much. But you do need to know for each quantum number, you need to know that the reasonable range that each one can follow. Okay. And they are based off of each other a lot. So when I do these, we got to know pretty well. So again, N is the energy level. I think that's pretty straightforward. So I'm going to skip over that one. For L, the value of L represents which quantum number, which type of orbital I have. So let's elaborate on that one. L can be 0. And if L is 0, what that means is it's an s orbital. An electron that has an L value of 0, we know that electron's in an s orbital. If L equals 1, that's p orbitals. Now, L just tells you that it's p orbitals, but it could be any one of the set. Remember, p orbitals always come as a set of 3. So when L equals 1, that means a set of p orbitals that are all together. Okay? Then if L equals 2, that means d orbitals. Okay? So, and again, if L equals 2, I know I'm in a set of d orbitals. And if you remember, I said the values of m sub L can go from, if L equals 2, m sub L could be -2, -1, 0, +1, or +2. It's not a coincidence that there are 5 different m sub L values when L equals 2. And we just happen to be dealing with d orbitals, which there's 5 of them. So if there's 5 orbitals, then I need 5 m sub L values, because the job of m sub L is to distinguish those from each other. So let's just say if I have like the 3D orbitals, so I'm drawing my diagram. So 3D orbitals, well, the 3 stands for the energy level, so that means that n equals 3. The D tells me the value of L. If I'm in a d orbital, that means that L has to be 2. And then m sub L, that's where I want to kind of label my orbitals. If I want to distinguish them, m sub L, if L equals 2, m sub L can go from -2 to +2. So I'm just going to like name these. Imagine like if I have 5 kids, I have to come up with 5 different names so that when I call out, hey, George, come over here, I want the right kid to come over to me. I don't want the other 4 to come. Okay? So here I'm naming my kids with m sub L values, and I have 5 choices. I can do -2, -1, 0, 1, and 2. So I'm just going to name them. -2, -1, 0, 1, and 2. I'm simply labeling my orbitals with different m sub L values to distinguish them from each other. Now, the actual order that I use is arbitrary, meaning it doesn't matter. Like if you put -2 over here or -2 in the middle, it doesn't matter. But if I'm comparing 2 electrons, if their m sub L values are different, then I know that they're in different orbitals. Okay, so that's the key. Excuse me. Now finally, when I put the electrons in, spin up or spin down, again, it's arbitrary. It's just your choice. But m sub s, let's just say I'm talking about this electron right here. The m sub L would be 2. And then the m sub s that's pointed down, most people would call that -1/2 or -0.5. Again, your screen can't see it. But so my m sub s value would be -1/2 or -0.5. Okay, so these would be the quantum numbers that describe that electron right there. Okay, now every electron in an atom, if you look at its quantum numbers, it's almost like your fingerprint. They say that every person in the world has a different fingerprint that could be used to identify them. The quantum numbers are like the fingerprint of an electron. If I have like a uranium atom that has 92 electrons in it, every electron will have a unique set of quantum numbers. So, some of the electrons might be in the 3rd shell, but some of them will be in sp or d orbitals, sp or d. Even if I say, let's just look at the d's, well, they're all going to be in different orbitals. So then I say, okay, well, let's pick this orbital. So if I narrow down the energy level, the type of orbital, and then the orbital itself, I'm still going to have 2 electrons left, but they're going to have opposite spin. Okay, so if I look at all 4 quantum numbers, every electron is going to be different if I look at the 4 quantum numbers. All right, so let's practice it some. let's just say I have a uranium atom. So uranium is number 92. All right. I want to know the quantum numbers of every electron. Well, we're not going to do them all, but let's do some examples. So the first electron. N. So again, it might be helpful if I'm doing this to kind of picture the electronic configuration. There's 1s2, 2s, 2p, 3s, 3p, okay, and I can keep going all the way up. All right, so that's my general configuration for the beginning of uranium. So the first electron is this one, okay? What's the N value? Well, N is the shell. That's the first shell. I'm putting electrons in the first shell, so N equals 1. L. Well, I put it in an s orbital, and a minute ago I said that if I'm in an s orbital, that's L equals 0. So L for the first electron is 0. M sub L. Well, the value of M sub L, the range can be from the negative value of L to the positive value of L. So M sub L can go from negative 0 to positive 0, which means it's 0. Okay? Now, if you think about it, an s orbital, if I asked you, I'm in the 1s orbital, and you said, oh, which one? You'd be like, well, duh, there's only one of them, right? So M sub L, there doesn't need to be any variation when I'm dealing with s orbitals because there's only one. M sub L only needs to have options when I have a set. So with a set of p orbitals, I need 3 M sub L values. With a set of d orbitals, I need 5 M sub L values. If I'm in f orbitals, I would need 7 M sub L values, okay? So those are my first 3, M sub s. So for that electron, most people say if it's pointed up, that's the positive spin, so 1/2. So those are the quantum numbers of the first electron. So then I say, okay, what about the second electron? How is it different from the first? So if I compare these two electrons to each other, how are they different? Well, the only difference between this electron and that electron is the spin. They're both in the first shell, they're both in an s orbital, they're in the same s orbital, but the spin's different. So my quantum numbers are going to reflect that. N equals 1, L equals 0, M sub L equals 0, M sub s equals negative 1/2. So I can see very clearly the only difference between these two electrons is the spin. So then let's jump to, let's say, the fifth electron. What would N be? So I'd say, okay, 1, 2, 3, 4, 5, that's that one. Now again, it really could be any of them, right? Because when we started doing this, when these were all empty, and we're filling our electrons up, the first electron could go in any of those orbitals because they're all equivalent to each other. They're degenerate orbitals. So the first electron could go in any one of them. So honestly, as long as you get the shell right, the second shell, and the p orbitals, the M sub L value, as long as you pick one of them, I can't count it wrong. Okay, so we'll get to that. But again, just realize that these electrons, you do not have to go left to right and label them the same way. That is up to the person who's doing it. We're arbitrarily deciding one orbital is going to be the X and one's the Y and one's the Z, but in real space, there's no differentiating them from each other other than just saying they're separate. So for the fifth electron, I'm in the second shell, so N equals 2. L, if I'm in a p orbital, that's going to be L equals 1. M sub L, again, this is where there's variation is allowed. M sub L, if I label these, if L equals 1, M sub L could be -1, 0, or +1. So as long as you pick one of those numbers, I have to give credit. Now, most people like to work from left to right, so we'll call that -1. But again, I can't count it wrong if you put 0 or +1 there. And then M sub s. Most people like to put the first electron in pointed up, but you don't have to. You could have put the first electron in pointed down. So again, you just pick. I'll just pick +1/2 because it makes everybody feel better. Okay? So those are the quantum numbers of the 5th electron. So then let's say, what about the 40th electron? So the 40th electron, if you look at a periodic table, it's in the D block, and it's on the 5th row of the periodic table. Okay, so I'm in the 5th row, so that means in the 5th row I'm going to be doing 5s2 and then 4d2. That's where I get to if I'm writing my configuration. I keep cutting off. If I'm writing my configuration of uranium, when I get to number 40, I've put 2 electrons in the 5s orbital, and then I put the next 2 in the 4d orbital, and that's where number 40 is. So I'm going to write the quantum numbers for that. Okay? So, N, if that electron is going into, it's the 5th row of the periodic table, but the d orbitals are always a shell behind, right? So if I'm in the 5th row, that means it's 4d. Well, the 4, that's the shell. N equals 4. L, if it's d orbitals, L equals 2. You just have to memorize that. L equals 0 is S, L equals 1 is P, L equals 2 is D, L equals 3 is F, L equals 4 would be G, L equals 5 would be H. Okay, and you can keep going as far as you want theoretically. So, M sub L. If I drew out the 4d orbitals, there'd be 5 of them, and I start putting electrons in, remember it doesn't really matter which one I put it into. So M sub L, as long as I put something between -2 and +2, it has to be okay. So I'm going to put -1. And then M sub S. Again, you have a choice. You can put the first set of electrons in all pointed up, or you can put in the first set of electrons all pointed down. Personal choice. So I'm going to go -1/2 this time. So those are the quantum numbers of the 40th electron. Okay? And for every electron that we do, we should come up with some difference between those. So hopefully you can practice those as you go. All right, it's a good place to cut off.